that works. Good. I understand. Yeah, can you hear me? Good.
Okay, thank you very much. Please go ahead, Christophe.
Thank you very much. So I'm Christophe Josserand. Actually, I will speak today about freezing impacts, and it is a common work with my colleagues since 6 years on this topic, Thomas Héon, and some student postdocs, and also that have became colleagues now. I'd like first to thank the organizer for two reasons. One is for organizing this nice conference. The second one is to invite me to talk because actually I was not here 5 years ago. And as you can see, I'm not speaking really on CI's mathematics or CI's modeling. The reason I'm here, I wanted to learn about this subject, and maybe the idea of my talk is maybe a break in this conference, and maybe it will give us reason to speak together or to exchange on this subject. So I will speak about something a little bit different, about freezing impacts. So maybe some motivation. So we have been interested since 5 or 6 years now on basically the coupling between capillary flows being obtained either by drop impact or by a flow around the surface, coupled with some freezing or solidification. That means you do that on a cold environment, particularly on a cold substrate, and you see how these capillary flows, so at very small scales, that is what is the difference between the CIs and our studies, and how these small scales, capillary flow at small scale, interact with the solidification. And I will present you maybe an overview of what we are doing with some details in some cases. Okay. So maybe a context which explains why I'm here and why I try to see how what we do could, in some sense, be connected to what you are interested in. So there are many contexts where solidification is coupled with flow, and particularly in environmental flow. So you see this ice cascade. You see also this ice structure that are formed in some cold caverns. You can see also some permafrost things. So when you have the soil that is very cold during winters, but then it melts during summers and so on. And you can see this large structure form. There are also an important application in industry, particularly on the icings of structures, particularly planes, where you have the ice that is formed on the structure, so it can perturb the flight, but also perturb the gauge that you use for planes. For instance, the gauge for pressure gauge could be affected if there's too much ice on it. We have also application in metallurgy, or now more modern one, which is 3D printing. For the icing problem of planes or even wind power, putting out the ice can cost a lot of money, but also cost a lot of products which are not very good for environment as well. Okay, so maybe a short story of freezing. Maybe the first people that mentioned somehow the freezing was Lamy and Clapeyroux, because maybe they are French, I'm citing them, but actually they were working for Russia at that time. And basically, they tried to understand the age of the Earth by thinking that the Earth was something that was a solidifying sphere of liquid, and they tried to obtain the age of the Earth by doing that. I don't remember what they obtained, but basically, it gives us the idea of what is freezing or solidifying. So you have a solid part, a liquid part, and then you have a front that is moving because you have some heat exchange. And as we all know, there is some heat which is needed to transform the liquid in solid or vice versa. Okay, so that became more mathematical problem when Stefan looked to that. So it's called now the Stefan problem, and at the end of the 19th century. So basically, he put in mathematics this diffusion equation in the ice and in the water, and then you have a boundary condition, which is the Stefan condition, that tells you that the difference between the heat flux in the ice and the water is taken into account for changing the liquid into ice or vice versa, depending on the sign of this quantity. Okay, so, and by doing that, if you have some, for instance, if you impose some temperature at the bottom of this problem, you obtain a square root of time evolution. You have a self-similar solution of this problem, and you have a square root of time with a coefficient that is obtained by some kind of implicit relation, or maybe depending on your boundary condition. So basically, we look to this problem again by putting now three domains: a liquid one, the ice one, and the substrate one. So now we consider also that the solid substrate can you have diffusion of heat in in the solids case, in the ice case, and in the water case. And if you do that, you still obtain a square root of rho a relation between the evolution of the thickness of ice as function of time with a coefficient. You need some assumption, but with a coefficient that is also depending on all these all the parameter, or the thermal parameter of the system. Okay, so we try to compare that with some very simple experiments. So the movie is not is a little bit dirty, but we did more clean movies. So basically we put together water in contact with a cold substrate, and then we measure the ice front that is growing with time. And you could measure by that, you could compare that with the square root law, and then you could get the prefactor of this square root law, and we could compare the prefactor of this square root law with the coefficient that we obtained from our 1D model. And if you do that, we have a decent agreement between the experimental measurement of this coefficient with the theoretical one measure without any, we have no, let's say, fitting parameter. It's the slope is 1 and there is no fitting parameter in our problem. Okay, as you know, there are another way in which ice can grow in a liquid, which is when the liquid is under cooling. So that means the liquid is below the melting temperature. And in that case, you can have the growth also of ice, which is somehow a different mechanism. It's not a different mechanism, but the source of heat that is needed to create the ice is not coming from the substrate, but more from the liquid itself. And there is this nice, so the water is under cooling, is in an undercool, and then you can see this type of ice that is going. And you see that in that case, you don't have a planar ice surface that is going, but more some type of peaks, which are called dendrites. And actually, this is also an old problem where people have looked to what is the growth of this dendrite as function of time when you have a liquid which is under the melting temperature. And with some assumption, you can show that there is a constant velocity of this. So it's not a square root of time. In that case, it is a constant velocity of the dendrite, which obeys some kind of law, experimental law, which the velocity of the dendrite evolve like delta T, so the difference of temperature between the undercooled liquid and the melting temperature to a power gamma, which is fitted from the experiment. Okay, so now let's try to see how we can use these general ideas to understand what we observe in some experiments that we have done. So the first experiment I will do is not drop impact, but drop deposition. So we basically, the question we were asking ourselves was, okay, you deposit a drop on a very cold substrate so that ice can be formed at the contact of the surface, and you ask yourself, will this ice stop the spreading of this droplet, and how will it stop? So there are different mechanisms that you can have in mind. Either there is a ice layer that is basically going as its own velocity inside the spreading drop, and it will maybe arrest the drop. You can have also ice crystals that are formed that maybe they will also slow down the spreading. Okay, let's do the experiments. So maybe I'll go a little bit faster. So the experiment is a very simple one. We have a water droplet, which is put on a glass plate, and we will put it in contact with a cold sapphire substrate. Sapphire is because it has good, it has good, it has good thermal properties and also optical one. So basically the question we are, how far does the drop spread in contact with this substrate, and how fast does the drop spread? I mean, there is how long it goes, but also what is the speed of that? How is the dynamics of this spreading affected? So let's look to the movies. So the first movie, so I call delta T the difference between the melting temperature and the surface temperature, the substrate temperature. So that means that if I have if delta T is 3.2, that means that my substrate is at minus 3.2 degrees. Okay, let's see the movie. So you see you have the spreading of the drop, and you end up with a given radius. Let's do the same experiment. Everything is the same except but the substrate temperature. And if you do at minus 10 degrees, you see basically something which looks quite similar, except again that you don't go as far as the initial. So you are arrested before the initial case. And if you go to even lower temperature, you are stopped much before and at a much smaller radius. Okay, if we put that on on a figure. So basically, you can make some assumption about the spreading. There are a law for spreading that has been derived by Behrens and Kere 20 years ago, saying that if you just consider the balance between inertia and capillary forces, you expect to have a radius that goes in time as square root of time at the contact. So if we look in our experiments to the radius as function of time, make dimensionless as this law, we observe a very nice agreement with at short time with this square root of time law. So the spreading at short time obeys this square root of time law, and then it is arrested at some point, and we want to understand why and when it is arrested. So this is for delta t equal -3, for delta t equal 3.2 degrees. If you go to 10 and 15.5, you see that somehow the short time dynamics is not at all changed, or very little change. So that means the temperature itself does not really affect the initial spreading, so the rapid spreading due to, in some sense, the contact line dynamics at short time. But it is stopped at a different length, at a different time, at a different distance from the origin, as you increase the difference temperature, so you decrease the temperature of the substrate, you are arrested much earlier, and in some sense you are arrested at a velocity which is higher. Okay. So if we now measure the radius as function of this delta t, so we could measure the arrested radius as function of temperature, we have this law, and using the square root of time evolution of r with t, you can transfer this radius as arrested radius as a velocity of arrest, typical velocity at which the system is dumped rapidly and stopped. And you have this law. And now we'd like to understand what sets and what controls this evolution of the velocity of the radius as function of the difference of temperature. So for that, we have, using the sapphire, we were able to look from below somehow to the surface in contact between the liquid and the sapphire. And what we observe, and you will see a movie after that, you observe that there are formations, it's not easy, some formation of like a crystal that is spreading along the surface. And you see that this crystal is spreading, and somehow when it reaches, so the circle here are the contact area between the drop and the sapphire, so it increases as time goes on. So here you have the time, and as time goes on, you see also crystals that are created, and when the crystal reach the contact line of the spreading, it somehow suddenly stops the spreading. So can we, and if you change now, this is as you change the time, now if you change the temperature, you see that this final surface of arrest is changing as function of the delta t, and as delta t is bigger, you see that it has a smaller contact area, but also this contact area has more, is more something that looks like a crystal than a circle. If you look to a movie, so let's try to see the movie, you can see that. So I don't know if you see correctly, but you see that there is the spreading, which is circular at the origin, but after the spreading, you can see that there are some crystals that are growing here, and when the crystal reach, for instance here, when they are in contact of the spreading contact line, they stop it suddenly. And we could actually measure as function of time the position of this crystal that is spreading, and you observe basically a constant velocity. So you have, in some sense, the spreading of the drop that goes as square root of time balanced by a crystal that grows linearly with time. So as you can imagine, that gives you a good, sorry, I'm going to tell it fast, but that good, in some sense you have the spreading of the drop with a velocity that decreases with time because it goes at square root of time, so the velocity decreases at square root of time, and it has to be balanced by the crystal that grows with a constant velocity. So at some point, the crystal will reach the spreading radius and it will stop the radius. And if you use this idea, you compare, and so now you could measure the velocity of the crystal from your experiments, and you compare this velocity of the crystal with the velocity of arrest of our contact line, and we observe that it goes well together over the bisectrix y equal x. So in some sense, we have our intuition that the crystal is arresting the spreading is the good one. That means that the velocity of arrest is on the same order, actually, in the same, is very close to the velocity of the crystal that you can measure. So that's it. And now, what sets this velocity? So now we have understood that the the spreading is arrested by the crystal that grows. But now what is the velocity of this crystal? As you remember, there is a constant velocity that you can measure when the liquid is undercooled, which is the one that you measure from the dendritic growth. If you put the dendritic growth velocity from the fit of the experiment, this is this curve, and what we measure for the velocity of the crystal growth and also of the arrest is much bigger than that. So in some sense, we cannot say that this is a free dendrite that is arresting the contact line. But in some sense, this is not that surprising, because somehow the problem we have to solve, which I think is an original mathematical problem to solve, it is how much does a dendrite grow on a crystal in undercooled liquid. So somehow you have to solve now this problem, which I think is interesting to solve, where you have a dendrite that grows in an undercooled liquid because the water is undercooled because it is in contact with a cold substrate, but also you have part of the heat that is pumped by the substrate. So in some sense, this system is much more efficient to grow ice than the ice alone inside an undercooled liquid, because you have a part of the heat that can be pumped by the substrate. So that explains why the velocity is bigger. And actually we are working on a model for understanding and computing the velocity of such a system. I will not give you the details on that. So a short conclusion on that, and I will go to some other thing after that. So we have shown that there is a race between the spreading of the spreading line and the solidification front, and this is what determines our arrest criterion. And we try to understand a little bit more what is the crystal velocity. I go a little bit fast because I want to discuss few different things that we are doing just to show you. So the title of my talk was drop freezing. So after drop deposition, now let's look to drop impact. So basically you have a drop that impacts a cold substrate and it spreads. And we look to that with a high-speed camera. So let's look first what happens when you have a drop impact on a room temperature substrate. So no freezing, the substrate is at room temperature. So you probably know this type of dynamic. So you have a spreading of the drop. I stop the movie now. So the drop has spread to its maximum diameter. And then after that, it retracts because the contact angle of the water on this substrate is has some value that you go to the final stage, which is this one. Now, if you do the same experiment with a substrate at minus 10 degrees, the initial dynamics looks very similar, except something different. So you have a spreading. The spreading goes to a maximum spreading, but after you reach this maximum spreading, you have a period that we have seen where the water is somehow blocked at this maximum spreading, and you have some waves that travels inside the water. So here, I stop the movie here, where you have, if you have to understand what is this state, it's a little bit different than the final state, the middle state of the other case. You have now a very thin layer of ice that you can see here, on top of which you have some water, layer, very thin water layer, which is blocked or attached by the contact line. If you wait a little bit more, what you observe is the water which is on top of ice is receding over the ice. So something which is not that trivial to understand, which is that in this case, you can see that water de-wets the ice, which is not something totally obvious. And if you go further on the movie, you end up with everything is solidified because your substrate is very cold, minus 10, and now you have everything is now ice. If you do the same thing at minus 30 degrees with the same velocity, you observe something quite similar at the beginning. So you see, you go to a maximum radius, then you have some waves that travels along this blocked system. So I stop the movie here. You still have some ice layer, which is probably more thick than the previous one, on top of which you have some water, and then you again have a receding. And what we are interested in this part is you observe that the final state is different. You see now you have a circle of water that is trapped and then solidified. And if you go even to higher temperature difference, you see a splash and you see some very interesting things. And if I have time to speak a little bit, you see also things that you might be interested in. You see some cracks in the ice that are formed by the dynamics. Okay, to make it not too long, so you see this nice crack formation while solidifying. Okay, so we could measure the profile of the final shape, the solidified shape of our impact. We can measure the profile. So you observe, in some sense, 3 types of profile. The first one is called somehow fried eggs. So you have to realize that you have a high ratio between this scale and this scale, so it looks much more like that. In this case, you have something which is much more like that, and in the later case, you have something which looks like that. So we measure the radius as function of time of the water extent. So if you do the impact at normal temperature, you have a very rapid spreading and then a retraction of the contact line, which is almost at a constant velocity. If you look to the same things at -7 or -24 degrees, you observe something which is not exactly the same for the spreading part, but very similar. Then you have something which is almost at a constant radius. This is the water extent, and this is the part where I showed you that the contact line was pinned by the maximum extent of the droplet spreading, and then suddenly you have a sorry, not suddenly, but then here you have the spreading of the water, receding of the water on the ice, which appears here to be at a constant velocity. Almost some constant velocity, which is very similar to the one on the substrate itself. Sorry. Okay, so just to show you that our very naive or simple model of growth of the ice in 1D is actually a good, can be a good way to understand the thickness of the ice that you observe in this experiment. So we could measure, we could decompose or solidified structure as a plateau things which has a thickness HP, and we want first to understand whether this HP could be understood easily. So in that case, we want to say, okay, if we believe that this is almost a 1D problem, it should be somehow, it should go like square root of D. The growth of this ice layer should go like square root of dt, and for the time, we could use the time that we just observed here. So we will measure this time of where the contact line is blocked by the drop. And we just compare this thickness here with dF, which is obtained by theoretical, it's an analytical solution, and we measure HP and we measure this time. And if we do that, we have if we then measure HP squared divided by tau, this time of contact. So if you measure the ratio between these two things, it should go, because HP should go as square root of D times T. HP squared divided by 2 should go linearly with dF, and you see that we have a good agreement and even a quantitative agreement, in the sense again we have no fitting parameter here. We use the theoretical value that you can deduce from the model. Okay, and now we'd like to understand why do we sometimes observe this and why do we sometimes observe this. So here the argument is quite simple. Basically, you have two time scales you want to compare. You want to compare the time scale due to the retraction. So you have a retraction of water on your ice layer, and in the same time, you still continue to have the solidification front that is advancing. And naively, you can say that if one is faster than the other one, if the retraction is faster than the solidification, you should end up with a circular structure. And if the solidification is faster than the retraction, you will stop the retraction before the end, and you will end up with a ring. So just to go fast, so we measure the velocity of retraction, which is almost constant whatever the temperature difference is, so which suggests that this is a visco-capillary velocity, so a retraction of. And then if we compare these two things, we can define two time scales. So I go a little bit fast on that. And what is interesting is that this time scale segregate or discriminate well the two behaviors. So here you have the retraction time scale, here you have the solidification time scale, and you can see that when this one is much bigger, so the time for solidification is much bigger than the other one. That means that you have time to retract totally before solidification, then you observe a spherical shape. On the other one, when your retraction time is much smaller, is much bigger than the solidification time, you are here, then you expect that you will be stopped before the spherical cap can be done, and you have a ring shape. Okay, so I want to discuss the last thing. So this work is for us very, we are still working on that, because in this work we have the question that I mentioned to you, which is the contact angle of water on ice, and we have some Pleasant work that try to understand a little bit better how we can define a contact angle of ice, how does it depend on the water of the ice, and on the temperature of the ice, and all that stuff. So I don't want to discuss that. I want to finish this talk, and I will then go a little bit faster by two things. One is another thing we are doing now is to show that for drop impact, the temperature of the substrate can have a much bigger effect, which is it can provoke the splashes. So you have the same impact at the same velocity, but different temperature of the substrate. And in one case, you have a spreading of the drop, a smooth spreading of the drop on the substrate. And actually, if you go to minus 70 degrees, you have a splash. And we have shown, and we have a paper that is submitted, that this is related to some hydrophobicity behavior of the substrate in contact with the water at this temperature. And the last thing I wanted to discuss in the few minutes is something, because I was watching to some of your of the talks here. There was the question of how the ice breaks and you know how we can break the ice. So here we are in a totally different context, but still we observe something interesting. So it's an older experiment, so the movie are not as good as the new one. But basically, we studied, the first study we did was impacting a drop on a cold substrate and watching to the final situation, as we discussed before. So here, the movie is much not as good. Here you see at minus 20 degrees, it's difficult to see, but there is nothing too much to see. But you have this ice that has been formed by the impact, and you end up with this ring that is formed. But we continue we take the movie much longer. And you see that the water here is still solidifying because you're in contact with a very cold substrate. And you end up with this structure, which is the one I called the ring before. Now let's do the same experiments, but at minus 31. So it's difficult to see, but this is not what is more important. So you see about the same thing. So you will see that here you will have also water. The water solidifies. And from now, you have no more water, you have only ice. The movie is still running, so we can wait a little bit. So you still have ice that has been formed at 0 degree, if you believe in the Stefan condition, that the ice is formed basically at 0 degree. But it was in contact with a very cold substrate. And you see at some point, suddenly, you see cracks appearing. Much after everything has been solidified, so there is no more water. And the last case I want to show you is minus 60 degrees, the same dynamics. And here you see cracks appearing at the beginning. You still have water. You can see, if you have good eyes, you can still see water that is retracting. And so you also have cracks. But in that case, you see that the crack are definitely, the geometry of the crack are very different. Here, they almost are orthogonal one to each other, while the other one, you could look like, it was looking like a fragmentation of the drop. And so we study that as function of the velocity of the impact, also the temperature, and we observe different regimes, basically three main regimes, except if there are some intersection between the regimes. So a regime where you have nothing, a regime where you see what we call fragmentation. You could see that the fragmentation, you have the feeling that it starts from a point and then it breaks everywhere, like you could see maybe when you break a glass somewhere. And the last one, you see hierarchical fracture is more something where you have one crack is appearing, then another one which is orthogonal, and so on. So some kind of a hierarchy. So again, since we are almost at the end, we use for that, because we use the model that you have mentioned, which is a Griffis model. So what is the idea of the Griffis model is that if you have a block of ice which has some conditions, you can ask yourself, what is the energy I need to break it in two? And this energy to break in two is you create two interfaces. So you have a surface energy, and since you create surface, you have surface energy to bring to your system. In the same case, your system, because it has been created at 0 Celsius degree, but you are still cooling your ice. Your ice has been created at 0 degree, but it's now at minus 10, minus 20. It retracts because of thermal retraction. But it is attached to the substrate. So something that retracts but is attached on one edge, we create some elastic energy. And this elastic energy, you want to compare this elastic energy with the energy to break it in two pieces or in many pieces by creating surface energy. So this is a typical Griffis argument of comparing surface energy of cracks with the elastic energy or some, let's say, energy of your material, which is a volumic energy. So by doing that, you obtain somehow a critical length above which it is better to do cracks or elastic deformation. I will just finish by that, but that gives us a good way to understand what we observe. So somehow when you are at a very, very low temperature, somehow this Griffis tank is much bigger than the drop, than the thickness of your spreading drop, so that you can create cracks very rapidly. So you create them before the water has been retracted. And when you are when your Griffis tank is much bigger than your thickness of your drop, you cannot create cracks. And in between, that is the interesting one, you have fragmentation. And I just want to finish with my conclusion. So basically, we observe this different fragmentation. And so you see there is the fragmentation of the drop, and the other one, which is the hierarchical cracks, are probably more related to something that you observe in desert, when you have some particles and dry particles, and you create cracks. Maybe that looks very similar to what we observe for the sea ice formation. Yeah, I think there are nothing to do together, but it's the image is nice. And I think I'm finishing here. Oh yeah, no, maybe the other thing we are doing is solidification, but I don't want. I think I'm a little bit late. Okay, thank you very much.
Thank you very much. Very, very nice videos, films. Thank you. Questions?
Thank you very much, Christophe. Many interesting regimes, and actually the much more. I remember that the impact with solidification of droplet, and finally spherical droplet makes a Christmas tree. Christmas tree,
yeah,
in the shape of Christmas tree. So that is because it's the solidification and also oscillation of the rest of the liquid. But my question is about the first part. Actually, it's spreading because of the surface tension. And you show that the solidification front moves along the substrate at smaller speed than the spreading speed of the liquid. So it seems that there is some delay of solidification. Spreading itself has not a constant speed, it decreases as per root of time.
The equality is not perfect between the speed of the contact line at the arrest and the crystal growth, because you need also to have a nucleation of the crystal, and then it has to catch up. So somehow you expect that the velocity of arrest is a little bit smaller than the velocity of the crystal, because you need some time to catch it. But if you take that it's consistent. So we observe something which is a little bit below, but the order of magnitude and more than the order of magnitude, the evolution is consistent between the two.
I have a small question. Can you go backwards? I mean, to your slide. Oh, no, the previous, this one. It seems that if you look at the outer edge of the fried egg, if you look at the outer edge, it has a constant teeth shape. So do you?
We try to work on that. We have no. That's actually, some people suggested us that maybe also the cracks could start from there, which is, I'm not sure. Sometimes you could see that some cracks are starting from there, but what is this wavelength is not.
You don't know.
No, we have tried. One of our students, there is, and we try to understand that. One of our students measured that. He has some data, but then the data they make a curve, but but we don't have any understanding of this curve.
Thank you, Christophe, for a really fascinating talk. I really enjoyed it. I guess I'm thinking an interesting generalization of your experiments, and something which would make it perhaps more relevant to seawater, would be to consider the freezing of drops with salt in them. So I think then you'd have diffusion of salt as well as diffusion of heat. and perhaps elements of mushy layer theory may come into the analysis. I think it could be quite interesting.
I agree. I agree. We haven't tried that here. Thomas is working with a student on the foam solidification, which is not that you have, but we are working more on let's say, structural water with some particles. But yeah, we should try with this.
One more, and then we need to have lunch.
Thank you for your presentation. It was really interesting. I was wondering if there was any insight on what are the physics behind the hierarchical factor.
Yeah, so that has been studied a lot for suspensions, drying suspensions, and this idea of hierarchical is in some sense you have a stress, you have the stress, which is you increase the stress as you dry the suspension, and then at some point you create a cracks, and these cracks somehow release the stress in one direction. So this is why you can have the next one will be orthogonal to it, roughly. So that's how people try to study these things by saying, okay, there is one crack, then another one which is mostly orthogonal. You may have also and you see it's not perfectly orthogonal, but you can see that definitely, it's definitely different than that. Here you have really the feeling that there is a wave, a cracking wave that propagates along your solid substrate. Here, definitely this is not a wave. You release the stress in one direction, to make it a little bit simple, and then the next stress release will be more in the orthogonal direction, and so on. And there is somehow, and then after you have done that at a large scale, then you have smaller scale that as the drying is going on. But I haven't looked in details how that goes in a self-similar. I think there are some self-similar dynamics related to that, but we haven't looked in details for that. And you can see, for instance, if we go back to our movie, you can definitely see the difference between that in this case you have one, they appear one after each other, sometimes almost at the same time, but you can see that somehow the cracks are separated one from each other. Why for this case? What is difficult in this case, it's so fast that you cannot really, but you see that there is one image, you have no crack, the next image, you have everything has cracked. And this.
Colder ice, or the colder substrate, if we can make it play again.
Yeah, I will, but I will finish this one because
okay,
on this because in this one also you can somehow say that there are some kind of length scale, which is probably related to the thickness of your ice layer. Why it's probably not the case here. Here it has probably something to do with the thickness of your ice layer, but not in an obvious way, because it's much larger. This thing is much larger than the thickness.
Yeah, but what do you think it depends on?
I haven't looked more enough. Okay. Yeah. I have to think. No, I haven't thought about that.
Thank you very much.
Thank you.
So now it's lunch and then free time. Then see you for dinner at 9:30, and please come tomorrow morning for another day of our workshop. Thank you. And thank you, Yuka, for sharing this session.